Alright, it's time for another math easy solution. We're going to discuss the shape of a can, basically the science behind the size and shape of the cans you buy in a grocery store, like pop cans and whatnot. This is actually an applied project question inside my calculus book, and you could basically click on this link here and you'll see that, and basically you'll get questions like this. You'll see where I got this question from. I found it really interesting, so might as well just do math easy on it. So basically, if there's a question as the shape of a can, this is an applied project, you have a volume of a cylinder kind of like this. In this project, we investigate the most economical shape for a can. We first interpreted this to mean the volume of a cylindrical can is given, and we need to find the height and radius that minimizes the cost of metal. You can see this figure, so we got to basically minimize this. We need to find the ratio of R to H that would minimize the cost of the can. So, and then if we disregard any waste material, if we just need to consider just the cost of the metal and there's no waste, then the problem, all you do is minimize surface area for, let's say, a given volume. If the volume is constant, let's write that down there. And then, so basically minimize the surface area. And I did this problem actually in one of my math videos. You can see this example too. They showed I did this one, and we found that it's H over, H equals 2R. And you could click on this link here. You could see my video where I prove this as well. And basically, if the height is equal to 2r, if it's equal to 2r, then that's just equal to the diameter. But the problem here, if you go out to your supermarket, as it says here, you'll see that the height is usually greater than the diameter, even though that the optimal one should be the same as the diameter. And the ratio of h over r varies from 2 up to 3.8. So you can write down here basically h over r equals 2 if there's no waste material inside, and h over r in real life varies from basically 3.8, and then from 2 to 3.8. It's never smaller than that. Usually never smaller than that. So now the rest of this project basically looks at explaining this phenomenon. Why is it between or greater than 2 if that's for no waste material? Well, let's look at the question 1 here. Basically, the material for cans, assuming let's say it's cut out from sheets of metal, and the cylindrical cans are formed by bending rectangles. So say if you have a can like this, you're going to have basically a cap here. So you're going to have 2 caps, or the top and bottom, and then this one right here is where it forms basically the cylinder part, and this is just rolled up rectangle. So you would just roll this up and you'll get something, you just get something like this. And this one usually has little waste, so we can just ignore that. And it says right here, these rectangles are cut out from sheets with little or no waste. Okay, but if the top and bottom discs are cut out from squares, because you still have to make these circular caps on the top and bottom here, but you got to cut them out of sheets of metal. So this is usually how it's this could be how it's done in the manufacturing one. And then, but if the top and bottom discs are cut from squares of sides 2r, as in the figure, in this figure the length is 2r. Just write that down. This leaves considerable waste, because you're going to have this stuff wasted. So you're going to have this stuff that's not going to be used, so that's just waste, all this stuff here, which may be recycled but has little and no value to the can makers, because for the guys making the can, doesn't really help. If this is the case, show that the amount of metal used is minimized when basically h of r is around 2.55. Well, in this case, we got to minimize the total metal used. So let's just say metal metal used in this case is equal to metal used equal to m. Let's just call it m, and this is equal to, well, the area of this, well, there's 2 of them, so we're going to have 2 times the area. In this case, is just going to be, 2r squared, plus the area of the cylinder part, in this case, this one here. And remember, the surface area of the cylinder is just going to be, it's just going to be the height times it by, the circumference here. Because if you flatten the circumference, you're going to get, this is going to be circumference, same thing. And the circumference of a circle is just pi times diameter, or 2 pi r. So we're going to have 2 pi r and then times it by h. Okay, so this function is a function of of r and h, but we want it as a function of m of r. So to do that, we have to get h in terms of r, and we'll get that by, well, we know that volume has to be constant in this project because we're just trying to vary r and h based on a given volume. And volume number is just going to be area of the circle times it by the height, and area is pi r squared times 8. This is of a cylinder. So then h would just equal 2 v over pi r squared, and we could plug this in there, and we will get m of r is equal to, right, yeah, basically you get over this one. So this is h in this case. It's going to be v over pi r squared. And simplifying this one, we're gonna get basically 8r squared plus 2v divided by, this cancels here. And now we just take the derivative in this case. We just take derivative here of r to get the, we have to basically minimize this one, and then remember it's gonna be at a local, at a local minimum or maximum. So we just use our calculus rules here. So we take derivative. This is gonna be 16r using power rule, and this one's gonna be, well, negative 2v over r squared. So we have this one here, and now we set it equal to 0 just to find a critical point, and then if we set it equal to 0, and we could basically solve this, and then from this we just plug in back v inside this one, so we'll have h and r. So if we plug that back in, we're gonna get 16r minus 2. This is the area, this is the volume here. Yeah, that's the volume is pi r squared times h in this case, and then as you can see, this cancels, we're going to be left with 16r minus 2 pi h, and then rearranging this one, we're going to get just 8r equals pi h, cancel the 2, divide by 2 and shift it over here, and then this one we're going to finally get h over r is equal to 8 over pi, and this is our answer right here. And there you go, and if you put in a calculator, you're going to get roughly 2.55. So this is roughly 2.55, and this is our answer here. So from this, we could see that if it was cut from squares like that, this is greater than the 2 for ideal. This is numbers ideal, no waste. So now this explains some part of it when you go to the supermarket, but why is there a range in the way it's cut? That's what we're going to find out further. Okay, so if we look at basically a more efficient way of packing this part of question 2 of the applied project is by dividing the metal sheets into hexagons. So basically we cut out in a hexagon-like form here, or how the sheets are, so that we can basically, it's more efficient than the other one, and we should get an h over r of 2.21. So we're supposed to minimize this one, getting it close to 2, because 2 is ideal with no waste. So this one is getting closer, so it's less waste than the square ones, but we gotta show this how it's true here. If we cut the lids and bases in from hexagons, remember the can's gonna be circular still, but we gotta cut it from some sort of metals here. So if we have hexagon metals, then basically show that the strategy is adopted. How it's this? Well, let's start it. So we'll do the same thing. Metal used, we'll just write it m equals 2. Well, the area of the cylinder part, that's just gonna be, well, circumference 2 pi r times it by h again, and then plus area of a hexagon, or 2 times the area of a hexagon. This is the top and bottom caps. And in my previous video, I showed that the area of a hexagon, if you have this hexagon, let's call this length t. This is from here to here, and they're all the same lengths, and the area is just equal to 3 over 2 square root 3t squared. So I showed this in my previous video. You could click on the Dropbox link below to see this, but we want this in terms of r here, and as you see, the inside circle, this one, this length here in terms of t, this just equals to, and again, you can see my video in the Dropbox link below on hexagon properties and the area. And I showed that the inner radius of this hexagon there, the r, is just going to be equal to square root 3 over 2 times t. So if we make this in terms of the area in terms of r, just take this part here, and this will be called, you take this area and just make it look like that's my mistake here. So we just square root both sides here. We gotta get a t squared in this case. So square root squared, this is gonna equal to 3 over 4 t squared. And t squared is equal to r squared times 4 over 3. Plug this in there. We're going to get a equals to Yeah, a equals to this one here. Plug this in here. This cancels. This cancels. It's going to be a 2. And this cancels. We're going to be left with... Okay, so we're left with this one 2 times square root 3 times r squared. Now we can plug this in there. So we're going to get m is equal to... Yeah, basically area of a cylinder. This is the sides. And then plus 2 times area of a hexagon here. And remember again, h, we look at the volume here. Pi r squared times h. Rearrange it to get this for h, so we could get m in terms of r, so we could take derivative. So m r is going to equal to, yeah, we're going to equal to this one. This is h here. Let's just simplify this, and we're going to get 2v over r plus 4 square root 3 r squared. This is m of r, so again we take the derivative in this case, and if we take derivative in this case, this is going to be equal to, well, this is just going to be negative 2v over r squared. This one, in terms of that, you could see my power rule video in the Dropbox link below to see this. And also this one here, this is going to be plus, well, 8 square root 3 in r. Set it equal to 0 in this case, then solve for r. We'll plug v back in, and we're going to get, yeah, we're going to get this one here with v, cancel it out, simplified, we're going to get, yeah, we're going to get this one negative 2 pi h, put this on the negative side, right side, negative 8, negative 8 square root 3r, so we cancel this out, we get, and divide this out, we're going to cancel this. It's going to be a 4, and we're going to get basically that this is going to be positive divided by that. H over r, bring this to this side, equals 2 4 square root 3 over pi. And this is what the answer that was given, that we had to prove here. And then if you plug in the calculator, you're going to get roughly 2.21. And as you can see, this is, it's yeah, greater than 2, but it's less than the 2.55, so it is more efficient packing than the yeah, than the square metal pieces where you have to cut off the circles from. So now if we look at question 3, the project basic values of h and r that we found, problems 1 and 2 are closer to the ones that actually occur supermarket values, but they still don't account for everything because there's still a lot more variations. If we look more closely at the real cans, we can see that the lid and base are formed, yeah, with the radius larger than r that are bent over the ends of the can, because you could actually see how you can see as on the cans you're gonna have a bigger radius here, and you can see how it's like wrapped around it when you see how it's joined around it by a larger circle around it. So you write that down. So you start with a bigger bigger circle, wrap it around the can here. So this is how they usually do it in the supermarket in real life. But if we allow for this, we would increase h over r because we're going to have basically a more waste material here. More significantly, in addition to the cost of metal, we need to incorporate the manufacturing of the can into the cost. So because basically cutting it from the hexagons and other circles, it's a bit harder than actually, you might have higher cost of manufacturing, so that's why they would do this. So let's assume that the most of the expense is incurred in joining the sides to the rims of the can here. Yeah, what this means is basically just joining the cylinder to the caps. If we cut the discs from hexagons, as in problem 2, then the total cost, it's proportional to this one here. This is the basic area of a hexagon plus area of the sides, and then plus this is cost, or this is reciprocal of the length that could be joined for the cost of one area of metal. Well, that's pretty complicated. Just consider it as cost per length of joining the sides to basically the, joining the sides to the caps, and in this case 4 pi r is basically 2 times the circumference. So it's, this can be 2 times the c around the cap. That's the length we're considering it, plus the height h, because you still have to join the cylinder when you wrap it in two. You still have to join it around. So we have this cost proportional to this, and now we have to show that this is minimized when you have this expression here. It's this kind of complex expression, but they have it in square root v over k, so you get basically volume over cost of joining. So this is kind of what it's proportional to, cost of joining, or cost of joining sides to caps here. Okay, so now we got to show that basically this little function here, let's call this m, is minimized whenever you have something like this. So let's just go over to this one here. We're gonna get, if we just take the derivative of this one, well, we first have to get h in terms of v. H is equal to v over pi r squared, like I've been doing above. So we're going to get m is equal to, m is equal to this one here. Remember, we're always changing the h because h is a variable here, but v is constant. So that's why we will put it in terms of v. So we have m in terms of r. We take derivative, just in case you didn't get that before. So we take the derivative here, m in terms of r. This is going to be equal to, well, this is going to be 8 square root 3 r plus this one here. Well, this one, if you simplify, it's 2v over r, so we just take derivative of this one here. Let's just put on r. R and r squared, same thing. I just interchange them. But so anyways here, so it's the same thing here. So take derivative of this one, we're going to get negative 2v over r squared. And then plus k over 4 pi, the derivative inside. And then minus, well, this is going to be a 2v pi r cubed using the power rule. Okay, so now this is the tricky part here, is basically writing it in a form of this one here. So as you can see, everything they've written is in terms of h over r, h over r, h over r here. So we have to basically keep in mind that, so we know that v is equal to pi r squared h. And if we write it in terms of h over r, this is going to be equal to pi r cubed h over r. Well, the r will cancel, get this one here. Just we want to write it in this term, so then the r cubed just equals 2v over, well, pi and h over r here. And then the r is just going to be equal to, this one's just going to be equal to right, v to the power of 1 over 3 over this one here, to put a 3 here, pi h over r, or just write it all in terms of the powers here. I like writing it like this. Now if we plug in this expression for r and r cubed inside this function, we're just gonna get prime of r is equal to, because remember we have to set this equal to 0, but we'll do that, actually we'll do that right now. We'll set it equal to 0 for getting the critical point of derivatives, and then also in this case I'll show later that all of them are minimized when these are 0. You can see from the functions. I'll show that in a bit, but basically if you look at this one here, put in this value of r, so we inside here 8 times square root 3. So we put this all in here. Well, you can see this is gonna be, this was r here, 8 times square root 3 times r, this negative 2v divided by, over in this case, well, I made a mistake here. Yeah, this is basically negative 2v divided by, this was r squared, so we just put in this formula for r, but then we square it, so we're gonna have v to the 2 over 3 pi h over r to the power of 2 over 3, and then we get all the way to this one. If we simplify all this, we're gonna get 0 is equal to, yeah, if we simplify this one out, we're gonna get, well, this one will stay the same here, minus 2, and to bring this one to the top here, and then this v's, this is gonna be 1 over 3, because we're gonna have a, well, v3 over 3 minus, divided by v2 over 3, and this just equals 2, well, yeah, v3 minus 2 is 1 over 3. You can see this on power rules in my link below here on the info link. But then, yeah, you get this one here, and this one also, this v is cancelled, this flips over, so we're going to get something like this. And next thing that you see that everything is a factor of 2, so we divide 2's everywhere. We're going to get now, this equals to 4. Yeah, we get it here, this one here, we take all the factors out. Also, made a mistake here, I copied from the wrong sources. This is actually a 3 here. You're gonna get that, yeah, if you ever try to solve this. Yeah, there's no square root there. It's a cubed root. It's yeah, and the link that you click will show the right one. I had the wrong one copied there, but regardless, so we keep doing this one. So now we have this one here. Now we gotta add these two up, because we could basically use the common denominator on this case, because we don't want this fraction there. Well, we want this to add it up. So we times this part by, yeah, by pi times h over r 1 over 3 on both sides, just so this one's going to add up with the power rules, so we get rid of this side here and we can add these up. So we're going to have 0 is equal to 4 square root, yeah, so we get this one here, this number, it's add up the power, so it's going to be just power of 1 there. And now we take the like terms out, in this case v 1 over 3, so we get 0 is equal to, yeah, we get this part here, and then plus, well, I'm going to actually put a negative here, just take a negative out, k, and then flip this around, so we're going to have this over r, just so it'll look like the equation we have. that we have to prove, and also because we're going to shift this to the other side as to be positive. Minus 2 pi here. So we've already done the negative switching here. So if we basically solve for v, we'll just divide by k, and solve for v 1/3 divided by k, we're going to get v 1/3 divided by k is equal to, yeah, so we get this final answer. This is actually the same as above, but I actually made a mistake here. This is 2h minus pi over r, and this is pi h over r. I had this switched around, but this is still the right answer. You could also just basically times by -1 and -1 on top and bottom, and we're gonna get equaling 2. Yeah, we'll get equal to 2, because if we put the negative here, we just switch this around, and we're gonna get 2 pi minus pi h divided by r, and then pi h divided by r, this one. So this is the right answer that we've derived here. Now we have it in terms of h over r here. So, and this is basically, that's what minimized when we have this expression here, because this is when the derivative is equal to 0, and in this case, and then I'm going to go back to why it's always minimized whenever we have the derivative. Basically, we look at the equation here, all these are positive values here, and it's all positive here, and then because you have this the square root here, when it's at smaller values here, this is actually going to cause it to go up. So all of them are going to have something like this. You're always going to have something like this one, and even going back to this one, m of r, this is positive values here. You have this divided by r here, so at small values, this is going to be insignificant. It's going to go to infinity. So you're going to have something like this always. And then this is always the critical point. You have this is when this is 0, when the derivative is 0, so that's minimum. And same thing for here. You're going to have this basically, m is in this case. So basically you're going to have this divided by r. Yeah, this one we have this one divided by r. Same with this one. There's a divided by r here. Yeah, so all of them have divided by r, so you'll have something like this, and this is always critical point at the derivative is equal to 0. Okay, so now that we have that, the question 3 solved, basically let's question 4 is plot this graph as a function of, we'll basically let x equals to h over r here, and use the graph to argue that when a can is large, or yeah, basically when a can is large or joining is cheap, we should make h of r approximately to this one here. Basically, so yeah, as in problem 2, but when the can is small or joining is costly, we should make it substantially larger. So to do that, let's just use Google, you just graph it with Google. Well, first thing to do, let's just write this in terms of x. So we have cubed v divided by k equals, do this one here. This is this is pi x cubed, and then 1 over 3. So 2 pi minus pi x, and then pi x minus 4 pi 4 square root 3. Actually, I made a mistake here. This isn't a pi here, so we have to get rid of this pi's in all of these areas. I'll show you why in a bit. I just made a mistake. So this one is the pi over, yeah, so again we will get, actually, where is this one here? Yeah, so we need to get rid of this one here. There's no pi's inside these ones in this case as well. This pi over, this one's gone there. Yeah, sorry about this one. This one is correct. So this pi is gone. I'll show you why I made where I made the mistake at. So we have to get rid of everywhere where there's an hr here, where there's a 2 pi minus hr. So this one again, get rid of this one here, and going all the way back to here. Oh, in this case here, because I showed you have to cancel this one out, because I showed that. Because when you go back up here, yeah, so you have this one here. This is what r equals to. R cubed is equal to this one here. And this function has a pi already. So this always cancels pi r cubed. This is r cubed v divided by pi over h over r. So we write that here. Actually, no, here. But then there's already a pi here. So we cancel. And then we're left with all the way back to this one. Yeah, so no, even when I looked at it wrong. So yeah, this is correct, and as you can see above in this equation, there is no pi here. So no pi. So yeah, that's just a little minor mistake I made here. So basically we plug this equation in. I plug this one into Google here. So we just plug this one here, pi times x to the power of, well, 1 over 3. I already wrote this one before, times 2 pi minus x all divided by pi times x minus 4 times square root 3. So if we graph this one out, so the graph should look something like this. Hopefully I didn't make any mistakes, but it should look something like this. So as you can see here, but remember that the volume always is positive and the cost is always positive. You're always gonna have a cost. So then it's gonna be greater than 0. Yeah, it's always gonna be greater than 0 here, and you're always gonna have a positive, well, square volume over. You're always gonna have a positive h over r in this case. So it's gonna be somewhere in here. So you only look at this stuff here as it's going to infinity, closer to it. So as you can see in this case, the limit is actually going towards 2 here. So you see where the x is here. So as you can see, it's getting closer and closer to 2. So the larger the material, the less waste you'll have. And when you go to close to 0, this is between 6 here. So if I write this back down, and if we just draw this, what we just graphed, remember x is equal to h over r in this case, and there's an asymptote here at 2. So this is 2 at h over r equals to 2 here. Remember, that's if there's no waste, and that's only no waste as you go to infinity large here, or infinity cost is, the cost is really small here. So then it goes up to basically around 6. This one is HR is around 6 in this case. It's roughly around this one here. But basically, as you can see here, and what we have to show is that when a can is large, or joining is cheap. So what this means is that as well, if you have this is equal to very, very small, very big, or large, then what this means is that your h over r is basically going to be really small here. So h of r gets smaller. And in this case, we should join it by the method we found by the hexagon ones. So then we should lean towards the hexagon packing. Yeah, so we should lean towards that one. And also, yeah, or it doesn't have to be necessarily hexagon packing, or you can have the bigger, the bigger radius circle and join it closer to it. So basically, we should get around 2.21. We should get smaller and smaller. But and also, if the cost is low, if k is low, then what this means is you're going to have a volume divided by, well, a low number. And remember, if you divide that by a low number, this is going to be equal to large. So if the cost is cheap, it's going to be up. And also if the volume is large, it's going to be up. But then if it's costly, if k is equal to, well, a lot of money here, is large, or v is small, you're going to have the ratio of the volume over k, the cubed one, that is small. So then as it's small, you're going to have a larger h over r is large here. So then we need to get a bigger h over r here. So what this means is that we're going to have if it's larger, this just means the height is bigger than the radius, so we're going to have it thinner and taller. And here we're going to have it basically stockier, or close to a kind of like a square. I mean, just draw more of a square like. So you're going to have it more like this shape from the side, and this one is more from like this. So when we have that, and that is basically what we just proved here from the graph. Okay, so now if we look at the final question here, question or analysis shows that large cans should be almost square, but small cans should be tall and thin. Well, this is, and if you take a look at relative shapes in the supermarket, this is usually true. So is our conclusion usually true? I say yes, usually, because you're not going to have a really tall, like a really large can that's going to be really, really tall, because that's just ridiculous. Yeah, like I've never seen one like that. But there are exceptions here, and there's reasons why you're going to have small cans that are not always tall and thin. And the reason is, well, this one, the answer is basically different materials here. If you have different materials, you're going to have different costs. Yeah, so you have different costs of manufacturing and costs of materials, because you have different materials. For, like, if you have plastic, you have aluminum or other kinds, and this equates to basically different, and you also have different properties of the material here, and different properties like and you could also basically, if you have different properties, you could also manufacture differently. So if you manufacture differently, what I mean by it, if you have plastic, you could probably just use a mold, and you could just do you could also use a mold, and this will just create a directly, just create the can right away, versus basically having to cut the sides and then you have to put the top and bottom on. So you can manufacture differently, and as technology increases, so companies may have better technology and so on here. So it depends, and also consumer wants. So it depends on what consumers want. If you want a really small but well, not that tall can, then if consumers want that, then you're gonna see that in the supermarket. Consumers' needs and wants. Well, that's all for today. Hopefully, you learned about this one. I could go on further, but this is a pretty long video already. But it's pretty random, but you might have to do this if your teacher makes you do this applied project. But regardless, it's pretty useful to, well, just pretty interesting to know how the shape of a can works, and you could use calculus to basically prove how tall large cans have to be usually square-like, and really small cans are really thin and tall usually. Well, that's all for today. If you learned a little about economics and can making, and you can remember you can download these notes in the Dropbox link below. Like always, you can click these links. You can see more on this. Well, that's all for today. If you learned, and stay tuned for another math easy solution.